Okay, here we go. It seems weird not doing this in front of an audience, but that's okay. So, linear algebra 1, vector operations. So we are doing vectors to start with. So we all know what a vector is. A vector is a quantity with magnitude and direction. Yes. So how do we label them? Oop, there we go. Vectors are either PQ with the half arrow on top, vector arrow. P is always the beginning, Q is always the end. That's if it's in point form. However, we do prefer to use the letters form. We have V for vector and V with an arrow on it. Generally speaking, this is what we're going to use most often. And we do it magnitude and direction. The magnitude is the length of the vector. And this is what we use for the magnitude of the direction. A and B are the components of the vector. Component form, speaking of components, what a vector would look like if the initial point was at the origin. So it would be a vector AB such that A is x minus x2 minus x1 and B is y minus y2 minus y1. It's always the second part of the coordinate. So if you have the point PQ, it's always the x coordinate from Q from the end of your vector minus the x coordinate from the beginning, the y coordinate from the end of your vector minus the y coordinate of your beginning. And then we will do some works with vectors. The scalar multiple of a vector. If vector V is multiplied by a scalar K, the result is a vector KV with the magnitude of KV is equal to the absolute value of K times the magnitude of V. In other words, if you multiply it times 2, it is twice as long. If you multiply it times -2, it is still twice as long, just going in the other direction. Okay. KV is either in the same direction of V or in the opposite. Yes, if K is negative, it goes in the opposite direction. If K is positive, it goes in the same direction. Okay, I'd ask if there are any questions, but nobody's here to ask any questions. For the points P and Q, find the magnitude and component form of PQ called V. Graph V in one color, then graph the scalar of V in another color. So we have the vector, we have a point PQ, sorry. And what we want to do is we want to write that in standard vector form. So I want to come up with V. So V, we need to find the components of V. The components are A and B. A is this is our start. This is our end. So we take the end minus the beginning. So it would be -1 minus 2 gives us -3. That's the A component of our vector. B would be same thing for our y coordinates, -4 minus -3, which is 1. So our vector V is the vector -3, 1. And if we were to graph that, which we will, this component vector always begins at the origin. We go out to the point -3, 1, -3, 1, which is here. Sorry, -3, -1, my bad, -3, -1. See, nobody's here to catch me on my mistakes. -3, -1, which is here. So there's our vector V. Okay. And if we want to do 2V, well, you just multiply everything times 2. -6, -2. And if we graph that vector, we go to -6, -2. And there is 2V. Piece of cake, right? Really easy stuff to begin with. So let's do this one here. Same idea. First thing I need to do is I need to find V. To find V, I need to find the components A. So A would be -2 minus 4, -2 minus -4, sorry, and I get 2 for that. Our component B would be 8 minus 5, 8 minus 5, which is 3. So our vector V is 2, 3. So I go out 2 and up 3. There's our vector v. And then if we want to do negative 3v, all we do is multiply those 2 points times negative 3. So I get negative 6, negative 9. And to graph that, I go to negative 6, negative 9. Oh, sorry, negative 6, negative 9 is down here. My bad. And there is negative 3v. Okay, moving on. Same idea. A little more complicated because I have fractions, but you know what? We are smart people. We can handle fractions. Our A component would be 4 minus 6, which is negative 2. Our B component would be 2 minus 1/2, which is 1 1/2 or 3/2. So our vector V would be negative 2, negative 2, 3/2. So I go ahead and graph that one, negative 2, 3/2. And then I want to do 4v. So 4v is 4 times those points. So I get negative 8 and 6. So I'm going in the same direction because I multiplied it times a positive number. So I go to negative 8 and up to 6. And there we go with that. And then last but not least on this one here, same thing. This one actually is pretty easy for the second part. So my A component is x minus x, 9 minus 9, which is 0. So it has 0 direction in the A and the x one, and my B is 9 minus 2, which is 7. So V is the point 0, or the vector 0, 7. So that provides my end point. 0 on the x, 7 on the y. So there's V. And then negative V is strictly multiplying it times negative 1. Negative 1 times 0 is 0. I get negative 7. So all that does is just flip it and point it in the other direction. Man, these videos are a lot shorter when I don't have an audience to stop me and ask questions. Okay. Vector addition. Fairly simple concept. If U is the vector AB and V is the vector CD, then U plus V is AC plus BD. Vector subtraction, as you could probably surmise, is you just subtract the components instead of adding the components. So U minus V is U plus negative V. So it'd be A minus C, B minus D rather than plus. It's actually pretty easy to do. So for the given vectors U and V, geometrically perform the given operation. That's an interesting thing. I'll show that first. Given the components of the resulting vector, and then give the magnitude of the resulting vector using color. So I'm going to graph these in different colors here. So first thing I'm going to do is I'm going to graph U in red, which is 4, 5. So I go over 4 and up 5. So here is the vector U. Now, when I'm adding vectors, I don't take the second vector V and I don't begin it at the origin. What I do is I begin it at the end of U. So from U, I go negative 2 in the x direction and up 4 in the y direction, which would take us to here. And there would be V. And then U plus V is this vector here. That would be U plus V. Now, I could have done V first, negative 2, 4, and then done U, on top of that. And if you look at it, what do I have? I have a parallelogram. This is often called the parallelogram method of finding the resultant vector. You make a parallelogram from the two vectors you are adding, and then the diagonal across from the origin to the point opposite that gives you the resulted u plus v vector. Now, what else does it ask for? It asks us for the resulting vector. So u plus v, add the x, 4 plus negative 2 gives me 2, and then 5 plus 4 gives me 9. And if you look, that matches up exactly what I have. And then it also asks for the magnitude of the resulting vector. The magnitude of u plus v is the square root of 2 squared plus 9 squared which is the square root of, let's see, 81 plus 4 is 85. And I'm just going to leave it as the square root of 85 because that's 5 times 17. That's prime. You can't reduce it anyways, and I don't want a decimal. So let's do the same thing on this next one here. So first thing I'm going to do is I'm going to graph u, negative 5, 2. So I go negative 5 and then up 2. So there's my u. And then I'm going to graph v. From that endpoint, I go over 7 in the positive direction and then down 9. So I go over 7, so that would be 5. That would take me to here. I need to move this. And then down 9 from that. So let's see, 5. Should be here. Okay. And so that's u, and that's v. And then here is the u plus v, adding them together. And once again, I could do the parallelogram method, which would put it sorry, 7, negative 9, and then u would be going back like that. And once again, there's my parallelogram method, having both u's and the v's in there. And my resulting vector, u plus v, add the x's, negative 5 plus 7 is 2, 2 plus negative 9 is negative 7. And then the magnitude of u plus v is equal to the square root of 2 squared plus negative 7 squared, which is the square root of 53. Okay, now we get things a little more complicated. So, once again, u, 7, 3. U is 7, 3, go over 7. 3, there's our u. And then I want to do v, but I actually want to do minus v because that's a minus in front. So rather than going over 9 and 7, I'm going to go negative 9 and negative 7 because I'm actually subtracting v. So geometrically, I'm actually subtracting v. So I'm going to do the opposite of v. So I would go negative 9 from here, which would take us to negative 2 on the x, and then go negative 7, 3 minus 7, which would take us to negative 4. So negative 2, negative 4. And that would be subtracting v. So there's u, there's v, and there is u minus v. Okay, so u minus v here. Because I do a positive u, and then I do minus v because I am subtracting v. And that gives me my parallelogram. Now, if I were to do the same thing and do v in the negative direction and then do u in the positive direction from there, I would end up with the parallelogram again. So my resulting vector u minus v is the vector, take the 7 minus 9, so I get negative 2, 3 minus 7, get negative 4, so there's u minus v, and the magnitude of u minus v is the square root of -2 squared plus -4 squared gives me, let's see, 16 plus 4 is the square root of 20, which is 2 root 5. If you really want to do that, I don't care. Okay, and here's our last example on this one. Ooh, this is a nice, relatively short video. So, once again, I do u. Although what am I actually adding? I'm actually adding 2u. So I need to do 2u. What is 2u? 2u would be 8, -4. So we need to go over 8, and then down 4 from there, 8, -4. Yeah. And so there's 2u. Not u, but 2u. And then I need to do from there 3v, but I actually need to do -3v. So that would give me -9. +3 would be what I'm doing from that endpoint. So from that endpoint, I go -9 over. So I'm at 8, so that would put me in -1. And I'm at -4, 3, so that would put me here at 1, 1. And that's -3v. And so 2u minus 3v is this little one right there. And let's double check my math. 2u is 8. So 2u minus 3v is vector 8 minus 9, so I get -1. -4 plus 3 gives me -1, so I get -1, -1. That is my 2u minus 3v. And the magnitude of 2u minus 3v would be the square root of 1 squared plus -1 squared, which is the square root of 2. Nice, short, simple, sweet. Thus endeth the lesson.